Welcome back, everybody. Hope everyone had a good weekend. We'll go ahead and get started back where we left off, which was talking about the continuity of piecewise functions. Just as a reminder, we have our exam coming up on Wednesday. The exam review has already been posted. If you haven't already looked at it, it's been posted since last week. The solutions will probably be posted a little bit later today, so that you can check your work and like if you were truly solving a problem, you can check it out then. Or you can attend my office hours, which are tomorrow from what is it? 12:30 to 12:30 to 2:50. Yeah. Any questions before we get started? Yes. We're gonna be finishing up unit 1.5 and then starting unit 2. So good news is there's not too much, like if you didn't print out the unit 2 worksheet, if memory serves, there's not too much like you'd have to like scramble to be nice and neat to transcribe. So, okay. So any other questions before we get started? Okay, so from last time we were talking about continuity, and the fact of the matter was that most functions are continuous on their domains. So when we were looking at this function here, we had to make sure we took into account part D, that is, we had to take into account the red and the blue. But if you're given a piecewise function, the issue kind of gets a little more difficult because on each piece you could be defined as a function. You will be defined as a function, and individual functions have their own discontinuities. But in addition to that, you also have problems at dividing values. So the step one was to find the discontinuities on each piece. So with this one, the issue with the first piece was supposed to be a red. Was both -1 and 2, but we were only defined as the top function for values greater than or equal to 0. So that -1 was not within our restriction, so it did not end up mattering. Our function actually is continuous at -1, which is strange enough, but that's because at -1 we're the secondary function, which is much nicer. And then for x less than 0, we're the polynomial that has no discontinuities because polynomials are defined everywhere. Now that we've checked the individual pieces, now we will check the dividing values. And so in order to do that, you need to check the left and the right-hand limits of the dividing values. So in this case, our only dividing value was 0. And so at x equals 0, we check the limit from the left and limit from the right. When you're approaching 0 from the right, you were the first function because you're equal to the first function for values greater than or equal to 0. And so then we plugged in 0 because we knew there was not going to be any issues, right? We weren't going to be dividing by 0 here. So we plugged it in, we got -5. We plugged in the left side, which would mean using the secondary function, the bottom function, and plugged in 0, we got -5. We got that they were both equal. Now, I told you guys that this was not enough. Why is that not enough? This is continuity, right? We're trying to show continuity, not just that the limit exists. So we also need to check that f of 0 is equal to -5. So maybe we should add this, remember to make sure f of a equals the limit as x approaches a of f of x. That's a last minute thing. Now, granted, these are long problems, so on the grand scheme of things, that might be worth like 1 point out of 10, but it is an important distinction. This just tells us that the limit exists, but our function could end up looking like this. Whatever it may be. But like it could end up looking like that, where you do have a limit at this a value, like whatever this a is. You do have a limit there. It exists. The limit exists, but the function does not. And therefore, it would not be continuous because you'd have to lift your pen off the page. So we do need to check that last condition. So f of 0 So, and f of 0, which function would I plug it into? Top one. Now, I know we already computed this. I do understand it. We already computed that up here, but here we were computing a limit. Here we're computing a function value. They end up being the same thing because the function is continuous, but that's not always guaranteed. I can show you an example right now after this. So f of 0 would be 10 over 0 plus 1 times 0 minus 2, which ends up being -5. So equal, therefore, continuous at x equals 0. So the function is continuous there. It's not differentiable, but we will get to that. We'll get to that. Therefore, continuous at 0. So with our dividing values, there were no discontinuities. So we checked step 2 was to determine whether or not you're discontinuous at the dividing values. Any questions on that?
Check for both the positive side, left side, and the x.
Exactly right. Because, so Esther was absolutely right. You need to check the left and the right because that will tell you whether or not the full limit exists. Because in order to have continuity, you need to have the limit to exist, the function to exist, and them to be equal to each other. So if we needed to check the left and the right hand limits because on both sides of the function of like both sides of that 0, that dividing value, excuse me, on both sides of that dividing value were a different function. So in order to check continuity, we need to check the left and the right to make sure that they equal the same number. Once we find out that they equal the same number, then we can claim that that limit exists. Then all we need to do is check the function value there and see that they're equal so that we can go on from there. So step 3. The final step is to combine steps 1 and 2. To determine discontinuity / continuity, depending on the situation. It might ask you for the intervals of continuity, in which case you want to pluck out all your bad x values and go from there, or you could just be asked for the discontinuities, in which case you just list the x values. So this one in particular was saying to find the intervals of continuity. So in the example, only point of discontinuity was x equals 2, because that was the only thing from part 1 was x equals 2, and then the only thing from part 2 was nothing. There was no discontinuity from part 2. So that is the only piece that has been plucked out, is a 2. X equals 2 is the only bad point. So if you're looking at a number line, here's 2. Everything else is fair game except for that number. Choose orange. Everything else is fair game, which means that it's continuous from -infinity to 2 parenthesis union parenthesis 2 to positive infinity. That's a long problem, but a very, very involved and good problem. And yes, you could memorize the process, but I'd rather you understand the intuition. Once again, the reason why we did it this way is we needed to check the continuity of each piece, because when you're graphing a piecewise function, if you remember graphing them, you end up having pieces that look like this. Like that. Right? There's 3 pieces here. There's the first piece, the second piece, the middle piece, and the right piece. Let me draw it better. Do this terribly. If you're looking at each piece, the left side and the right side, totally fine, totally continuous. You can trace those pieces without ever lifting your pen from the page. The middle piece has a discontinuity in the middle because if you were drawing just the middle piece, you'd have to lift your page up right here and continue back. So there was a discontinuity on a piece. And then furthermore, we have to check the dividing values because the dividing values are places where you switch functions. So on here, we do have a discontinuity at this dividing value because we have to jump to start over. But here, we don't have to jump. We just end up filling in the open circle that we drew. Does that make sense? You can memorize the process if you want to, but I'd rather you understand the intuition behind it. So, case in point, by the way, how I could have made it so that you do have to check out. What if this had instead been this? X, oh. So just to pay attention for a second. So X greater than 0. And then let's just say for the sake of an argument, it equals 2 if X is equal to 0. Then what that function ends up looking like, just in the interest of time, so you have -5 right here, and then 2 up here. So you'd end up having a solid, like you'd end up having a limit that exists, but you'd end up being that f of 0 is equal to 2, and they would not equal the same thing. So that is why we need to be careful, and we should check to make sure. Is it super, like most of the time it ends up just working out, but that's besides the point. Let's do another one. Let's do a kind of more involved one. This one right here, 2 dividing values. There's -1 and then there's 4. So now instead of having to, like, yes, it took a long time to do that problem, but that was also because we were writing out the procedure. Now I'm going to show you how you can do this without writing the procedure. So, but I'm still going to follow it. Step 1. Intuition is that we're going to check each piece because on its restriction, each piece on its restriction. So for x less than -1, f of x will equal -24, and I'm going to factor it right here. This ends up factoring nicely to x minus 5 times x plus 3. Once again, if you haven't been practicing your factoring, if that was hard for you to figure out, that's an indication that you should spend some time like practicing your factoring before the exam. There is going to be factoring. So for x greater than or x less than -1 strictly, our function looks like that. Now that function, if you were to just ignore, if you were ignoring this, that condition, you're looking at that function just by itself, looking at nothing else besides that function is discontinuous at 5 and -3. This function is discontinuous at x equals 5 and -3 by setting the denominator equal to 0. However, one of those can immediately be gotten rid of. Which one? 5, because that is a value that is not within our restriction. Our function is only defined as this function, this top function, for values less than -1. So that 5 is not in the restriction. Because we are not in that because our function is only defined for values strictly less than -1, that 5 is not even going to show up for this function. Next, for -1 less than or equal to x less than 4, f of x will equal 2. And that function is a constant function that has no issues. You're not going to be finding any value where it's dividing by 0. Not going to find any places where you're going to be taking the logarithm of a negative number because it's just a constant. So no issues. No issues. No discontinuities. For x greater than or equal to 4, our function will be -x squared plus 26. So when our x values are larger than or equal to 4, our function is the downward facing parabola. Our parabola is continuous everywhere. Yes, parabolas are continuous everywhere because they're polynomials. They're the second degree polynomials. And so they are continuous everywhere, which means that they are definitely continuous on x values greater than or equal to 4. So no issues. No discontinuities. So the only discontinuity we had from the pieces themselves was from the first piece. So we only got one discontinuity so far. Any questions on that? That's step one. We've checked every piece. Now we check the dividing values. For x equals -1. We'll do that. And also, if it helps you at the end of the day, maybe write down after step one, write down all the discontinuities that you found, just in case you're trying, like, because it's going to be like, this is going to be slightly long. It's a longer problem. So it's good. Just, do you guys remember solving systems of equations and how much work you had to show? And it's kind of hard to parse back through your work and find out what x values you found or y values, whatever. Same idea here. Like, it doesn't hurt to underline, but either way. For x equals -1, we're going to check the left-hand limit, the limit as x approaches -1 from the left of f of x. Which function would I be? Top, middle, or bottom? Top, because we're approaching -1 from values slightly less than -1. So this would be the limit as x approaches -1 of -24 divided by x squared minus 2x minus 15. And so that will be -24 divided by -1 squared minus 2 times -1 minus 15, which will be, let's use our calculator. That's going to be -24 over 1 plus 2 minus 15, which gives you 2. And just as a reminder, I was able to plug this number straight in because I knew from my factorization in part 1 that -1 wasn't going to be an issue. I wasn't going to be dividing by 0 by doing that. So I knew I could just plug it in and just drop the limit sign, so on and so forth. Next, the limit as x approaches -1 from the right. If you're approaching -1 from the right, let me write that better. You're going to be using the limit as x approaches -1 from the right of just 2, your constant function 2. And the limit of a constant is just the constant itself. So these are equal. Which means that the full limit exists. Yes.
The middle where you have -24 over x squared.
Uh-huh.
Yeah, right there, the x to 1, the x to -1 is supposed to have a negative next to it.
Oh, yep, you're right. You're right. Thank you. -1 from the left. Thank you. If like if you weren't if you didn't see what the student was talking about, there was supposed to be a minus sign there. We're approaching it from the left. My bad. Thank you. Thank you. So the full limit exists. That's not enough. Remember, that means that the limit exists, but we also need to check the function. So that's part, and then f of -1, because the function is defined is just 2, because at -1, your function is the constant function 2. So they're equal. I'll even write function exists. Smiley face, which means that it's continuous at -1. Function exists, the limit exists, and they're both 2, so it is continuous then. Up until checking that the limit was like, if we just check the limit, we don't necessarily know what's happening, especially because a curveball can be thrown. It could be this, in which case the function isn't defined at -1. If we make that middle term, if we make that middle restriction just a less than x less than 4, -1 less than x less than 4, then the function doesn't have a value at -1. That would become an issue. That's the reason why we do need to check those things. Next, we'll check it for x equals 4. So the limit as x approaches 4 from the left of f of x. In this case, we would be using the middle piece, the middle function. That's what the function we would be using. And the middle function was the constant function. So that will just be a limit of 2, which will be itself. Secondary, limit as x approaches 4 from the right of f of x. In this case, we would be the final function. We would be the bottom one because we're approaching 4 from the right, so slightly larger numbers. And so that would be the limit as x approaches 4 from the right of -x squared plus 26. And that is a polynomial. And polynomials are defined everywhere, and they're fine everywhere. So you can just plug in that 4 without having to worry. If it was -x squared over 26, and then we also had an over x minus 4, that would be cause for concern, but it's not. So we can just plug it in. So we get negative parentheses 4 quantity squared plus 26. That's -16 plus 26, which is +10. And these are not equal. The left-hand side was 2, the right-hand side was 10. Because the left and the right-hand limits do not agree, that would mean that the full limit does not exist. The limit as x approaches 4 of f of x does not exist. And if the limit doesn't exist, it's discontinuous. And x equals 4. So we don't have to go through and actually check the last condition. We don't have to check that f, you can verify it for yourself. F of 4 exists and equals 10, but that's not enough. We need the limit to exist, the function to exist, and then for them to be equal. Yes, the limit, like the function does exist at 4, but its limit doesn't exist. So we're done. Any questions on that? It's a long process, especially when you have 2 dividing values. And so, combining everything, unless there's any other questions. Which it's okay if there are. Clear? The question this time, be careful. The question here was saying find all x values of discontinuity for which the function is discontinuous. So we don't need to write an interval. Question's asking x values of discontinuity. So the answer should just be x equals -3. Sorry, I don't have it in front of me. -3 and then -1 from the secondary piece. And that's it. That's our answer. Any questions on that? So always be paying attention to the verbiage. It might just ask for where it's discontinuous. It might ask for the intervals of continuity. They're two sides of the same coin, but depending on the situation, you want to answer it differently. Yes. Four, excuse me, four. Thank you. Thank you for catching that. Sorry. Always question what you're learning. Thank you. Right. So it was continuous at 1. And that's why, honestly, that brings up a good point. That brings up, so I legitimately, I was going against it. I know myself, I should have just underlined this and underlined this to remind myself when I'm looking through, those are the points. Does that make sense? I normally do that, and I don't know why I didn't do it this time, because I know myself better than that. I don't trust myself to I don't know about you, when I'm taking a quiz or an exam, I black out a little bit. I just start going in the zone, and I'm not even really paying attention to what I'm doing. You guys remember Old School, where he does the speech, like the speech and debate scene? If you have it, it's a silly movie, grungy, like you don't have to watch it if you don't want to, but there's a scene where Will Ferrell starts doing a discussion against for speech and debate, and he blacks out and just has an excellent response. There's a question. Yes.
So where the exponentials.
Excellent question. So we picked x equals -1 and x equals 4 because they were the dividing values. Which one we choose to do first, like the limit, like if we choose to do 4 first, that's our prerogative. So there's no rhyme or reason as to why we chose to do -1 first. I was just looking top to bottom. If we were an alien species, or an alternate dimension, and we read from bottom to top, then we probably would start with 4. But just I did it based on convention. And then which one I choose to go from the left to the right first does not matter, as long as I check both. Okay. Now we get to the really fun problem. Well, this one is not as fun as the next one, but it's still very fun. So find a constant k such that the function below is continuous everywhere. Find a constant k such that this function is continuous everywhere. Okay. So we need it to be continuous everywhere. K is just a constant. We don't know what it is at the moment. We do not know, but it's just going to be some number. Could be 5, could be -3 billion. We do not know. So we'll just treat it as an arbitrary constant for now. And we'll go through the motion. Yes, it's a different problem. We haven't seen it before, but that's not a cause for concern. We still go through with our main process and see if it works. If it works, awesome. If it doesn't, it doesn't. So step 1 is to check the dividing values, or the pieces of the function. For x greater than or equal to 1, f of x will equal k e to the x plus 2. For values greater than or equal to 1, the function will be some constant, whether it be 7 or -5 or whatever it may be, e to the x plus 2. Does that function have any issues?
No.
No, because it's an exponential. Yes, that k is weird. Yes, I get it. But that k is nothing. That k is just a number. It's not going to be making us divide by 0. It's not going to be taking the square root of a negative number. So we're fine with it. No issues. So no discontinuity. That's good. There wasn't something we needed to do to k here to make sure that this thing works out. So that's good news. For x less than 1, f of x is equal to 2x plus 1. Same issue, same thing. No issue, no issues, so no discontinuity. Because for values strictly less than 1, your function is the line 2x plus 1, and lines are polynomials, and polynomials are continuous everywhere. I mean, lines are continuous everywhere, but it's because they're polynomials. Just not very exciting polynomials. Any questions on that? So that step has been taken care of for us. We don't need to worry about making K work for anything on the inside of its restriction. So we move on to step 2. We need to check to make sure that it's continuous at its dividing value. And this is where the bulk of the issue is going to come into play. For x equals 1, that is our dividing value. The limit as x approaches 1 from the right of f of x is going to be the limit as x approaches 1 from the right of the top function or the bottom function. The top, because we're approaching 1 from the right, larger than it. So the limit as x approaches 1 from the right of k e to the x plus 2. And you might be freaking out a little bit, and that's understandable. But if you remember from unit 1.2, what we had talked about at the very end is that the limit only cares about the variable in question. The limit only cares about the variable it deals with. This is the limit for the limit, it's only worried about x's. The k is some number that it does not care about. As far as it's concerned, it's 7. It's not actually 7, but for all it's concerned, it's some number. So when you plug in 1, you're just going to be plugging it in for x, and there's no issues. You're not dividing by 0. You're not taking the square root of a negative number. So we can just plug it in, and we get k e to the first power plus 2, or preferably k e plus 2. E is just a number. It's 2.714, I think-ish. It's an irrational number. Very important number, but it's just a number. And here's where you might see where the issue is going to lie. Maybe you're already seeing what the problem is. Try and see what the problem is going to be. That's one side of the limit. Let's check the other side. The limit as x approaches 1 from the left of f of x. This would mean you're in the second function, the bottom function. That's the limit as x approaches 1 from the left of 2x plus 1. And that's a line. We've already talked about how that's continuous everywhere. And there's no dividing by 0, no nothing like that. So we're fine to just plug in the value and drop the limit sign. So this becomes 2 times 1 plus 1, which is 3. So one side of the limit is k e plus 2, and the other side is 3. That's not good because those aren't the same thing. However, we're trying to find what k is. So we need these equal. Otherwise, not continuous. We need these equal, otherwise we're not going to be continuous. And the whole goal of this problem is to find the constant k that will make this function continuous everywhere. We've checked the pieces already. They didn't cause any discontinuities, so that didn't affect what k was equal to. And now we need to check the actual dividing value, of which we found that the left hand limit gives us a finite number, and the right hand limit gives us also a finite number, but the ability to solve what k is. So that means that ke plus 2 is equal to 3. And that's not too terrible to solve because e is just a number. So we'll subtract 1 and divide by e and get that k is equal to 1 over e or e to the negative 1. However you want to do it is fine. And that will be the value of k that makes this function continuous. Highly recommend trying to plug in to your calculator this function here, or have Desmos graph it. If you need help with Desmos, please let me know. I have used it extensively. But if you graph this and try different k values, you'll see that depending on what k is, there'll be a jump or a jump above or a jump below. And then finally, if you plug in 1 over e for k, you see that they connect at 1. And then you actually have a continuous function. Any questions on that? Do you have one? Okay. Now, there is one thing that I am glossing over, technically speaking, And I'm going to write that down. Technically speaking, we should make sure that f of 1 exists, but seeing as f is defined at x equals 2, at x equals 1, we should be good. If we want to be fully correct, what we would also check to do is we'd also check that is f of 1 is equal to 1 over e times e to the 1 plus 2, which is going to equal 3. The e's cancel and just give us 1. So you can check your work here. Technically speaking, you should, but these problems end up being very involved anyways. So basically by virtue of the function being defined well enough, we can usually kind of skip that part. Any questions on that? All right. Most fun problem, and then we're done with this unit. Find constants A and B, not just a constant K, but a constants A and B, so that the function below is continuous everywhere. So technically speaking, we should, like, once again, we're approaching a new situation. We haven't seen it before. Let's try our main process that we've learned and see if it works. If it works, awesome. If it doesn't, we'll try something new. But it's not no harm, no foul if this doesn't work. But step 1, just in the interest of saving space, no issues. No issues on any piece. 7, constant function, totally continuous. 5, constant function, totally continuous. Cosine and 2bx, those are both defined everywhere. We're not going to be dividing by 0 or anything like that. I know it looks kind of wonky, but cosine is a continuous function. We're not dividing by 0. We're not taking the square root of a negative number. We're not taking a tangent of a number that doesn't exist, or a secant or a cosecant. It's cosine, and cosine is defined everywhere. So there's no issues on any piece. So instead, what we have to do is we have to go to step 2. And for x equals 1, we'll do the left and the right hand limits. The limit as x approaches 1 from the left of f of x is going to be the limit as x approaches 1 from the left of 7, which will be 7. By the way, if you do feel comfortable and just plugging in the value, like writing down this, like you could either start here and go straight to the answer. Like, let me let you write it down before I make you look back up. You could either go straight from here to the 7 if you wanted to, if you feel comfortable like looking at the function and saying, okay, top function 7, no issues, plug in 7. Or you could go straight to this. Like, I know what the function is going to be for the value from 1 to the left, so I'll just plug in the function immediately. So in the previous example, in this one that we just did, if you know, like, you could skip this step and just write this. Do you see what I'm saying? Or go from here to here. And that would be sufficient. But anyways, so the limit from 1 from the left was 7. The limit from 1 to the right of f of x I'm just being very, very careful. I'm just showing every step. But once again, if you feel comfortable skipping a few steps, please mind my guest. Limits as x approaches 1 from the right of a cosine of pi x plus 2bx. And I know, get it, that looks intimidating. But pi is just a number. And a and b are just numbers. We don't know what they are yet. They could be 5 and 7, could be -2 and -1, who knows? But they're just numbers. So since we're taking the limit as x approaches 1, the a and the b are just ignored. So this becomes cosine, or a times cosine of pi, because it'd be, or I'll write pi times 1. And then plus 2b times 1, which will be -a plus 2b. Any questions on that so far? So let's take a second to reflect on the problem and see what's going on. Because last problem, when we did it, it was like, okay, we needed to set those two things equal to each other. And that's true here. We need these equal. So we need -a plus 2b to equal 7. That is true. But we look at this and we say, well, that's two variables. So there must be a way to remove a variable. What do? I haven't finished, so maybe looking at 2 as well will give me something else. So let's check 2 as well. For x equals 2, the limit as x approaches 2 from the left of f of x will equal the limit as x approaches 2 from the left of ax, or a cosine pi x plus 2bx. Sorry, it's scrunched. I need to give you guys more room on this problem. Sorry about that. We still got a little more to do. 2 from the left, we're talking about using the middle function. And once again, a and b are just numbers, so the limit doesn't care about them. So we just plug in 2. We end up with using the wrong type of pencil. A cosine of pi times 2 plus 2b times 2, which ends up being a plus 4b. Because remember, that would be cosine of 2 pi, and cosine of 2 pi is 1. You can use your calculator. Once again, please remember that your calculator should be in radians. Speaking of which, my other for the other class that I teach, I have to we talk about only degrees, so I just need to make sure my calculator is back. So that's the left-hand limit. Then we'll check the right-hand limit. X approaches 2 from the right of f of x. That will be the limit as x approaches 2 from the right of 5, which will just be 5, which means that that will be our limit. We need these equal, meaning that we need a plus 4b to equal 5. Aha! There we go. We have 2 equations and 2 unknowns. We can solve that. If you only have 1 equation and 2 unknowns, you can't solve it. Like if you have x plus 3y equals 7, there are infinitely many solutions because it's a line. But if you have 2 equations with 2 unknowns, you have 2 lines that will intersect somewhere. Or they could be parallel, or they could be the same line, but that's besides the point. So we're good. We got this system of equations. -a plus 2b equals 7, and a plus 4b is equal to 5. Any questions on that so far? It's a tricky process. Don't get me wrong. But a very cool problem. At least my perspective. And however you want to solve a system of equations is your prerogative. I would recommend elimination to be the best option, or the addition method. Some people call it the addition method, some people call it elimination. You can use substitution, right? Solve for A in whichever one and plug it into the second one. But I think hopefully you guys see that elimination is the best option here, because you've got a negative A and a positive A. So they already have the same coefficient with opposite signs. So all we need to do is add them together. And that'll cancel the A's. We get 6B is equal to 12, which tells us that B is equal to 2. And then we can use either equation to solve for A. It does not matter which one. Which one do you guys want to use? First one or the second one?
Why did you put them together?
So I was rewriting them as a system of equations. And that's the reason why I paired them together. And then I'm using the elimination method, which is where you're trying to eliminate one variable. And you want the variable that you're trying to eliminate, you want them to have the same number but opposite signs, so that when you add them together, that variable cancels and you're only left with one variable.
Because they need to be together to find what B is. So
Yes, exactly right. So I mean, the other way to do this, by the way, thank you for bringing that up. So the other way to do this would be to take that negative A. So you have negative A plus 2B equals 7, and you have A plus 4B is equal to 5. You could solve this one saying that A is equal to 7 minus 2B. Bring the A to the right-hand side, subtract the 7. Sorry. I got ahead of myself. 2B minus 7. And then you could plug this in for A. You'd get 2B minus 7 plus 4B is equal to 5, which would end up giving you 6B is equal to 12, just like normal. So that's another way to do it with the substitution method. I'm okay with either. Both are valid. I just find that the elimination method works better with me. Here's the substitution method. And now that you have A or B being 2, you can use either equation to solve for A. I'm just going to use the first one just because, but it doesn't matter. So negative A plus 2 times 2 equals 7. That'll be negative A equals 3, which gives us A is equal to negative 3. So we can rewrite it if we want to. A is equal to negative 3 and B is equal to 2, but either way is fine with me. We've underlined our answers, so that would be also acceptable. But if we want to have them finite, we'll put them together. And I guarantee you, if you plug in those values and draw this function, you'll see that finally they connect. If you make A equal to negative 2, you'll see that the middle piece starts to get wonky. And you'll have 2 jump discontinuities. Any questions on that? Cool problem, though, I hope. I hope you guys liked it. Systems of equations coming back with a vengeance.
can you go back up to the total to show that it's
Sure. Is that okay? Yes.
So everything we're doing in this problem is in radians.
Yes, everything should be in radians. For our class, legitimately make sure your calculator is always in radians, because that's the only degree measurement we will use is radians. For angles, we will only use radians in this class. Yes.
So we ever be dealing with discontinuities with this problem and the last problem?
So, no, because like then it becomes a far more complicated question. Because then you have to have you have 2 conditions that need to be satisfied by one variable, which can be instead of having 2 conditions that need to be solved by 2 variables, you'll have 2 conditions that need to be solved by 1 variable, and it will become a problem. So, but just to show the correct terminology and saying we need to make sure that it is continuous on those pieces, we should, but it's not 100% the issue. If you just skipped that and moved on to step 2, if this was a problem on your quiz or on your exam, I would be fine with that. I'm not going to get super caught up with that detail. Okay? Any other ones? So we're going to omit this problem. Just please ignore. We're not going to talk about the intermediate value theorem. Very, very fun theorem. If you'd like to know more about it, please feel free to ask. But I just don't want to waste, not waste time. I want to get us started on unit 2. So I'm going to skip it. You're not going to be tested on the intermediate value theorem, so you don't need to worry about that. But once again, if you want to know about it, please feel free to ask. And that will complete unit 1.5. All right. So let's go ahead and take a break until 10. And then we'll get started up with unit 2. People watching the recording, go do some guided meditation. All right, we're back. So that was the end of exam 1 material. So exam 1 will cover up till then, not including the intermediate value theorem that wasn't necessary, that was omitted. So that will be the end of unit 1 material. Please make sure you're studying up for it. The exam review, as I said, is already up, and the solutions will be posted a little later. And now we'll be moving on to unit 2 material. So for exam 2, which is derivatives. So very, very, very fun stuff. Exactly right. It's this is where we're gonna start really, really snowballing. So just be prepared for this. I know, like the weather's gonna start getting nicer over time, and we're gonna want to spring is a tough semester because it starts to get nicer out, and we want to just enjoy that time period. Please stay keep your ear to the or your nose to the grindstone in this situation, because these things do build on each other very quickly. So 2.1, the definition of the derivative. So how did it come to be? How did we figure out what the derivative is? And more specifically, what is the derivative? So from P-Calculus, you might have heard of the terminology of the average rate of change, or the secant line, which is done by taking 2 points on the curve and find the slope of the line connecting those 2 points. So it was written usually like, wrong size font, M sub secant, or average AVG, is equal to F of B minus F of A over B minus A. That was the secant line. It's just the slope formula, but just written differently because we're talking about a function instead of just a line. That's the reason why it was kind of written slightly differently. And what that is, in an intuitive, in a real world sense, that's like the average rate of change. So if you're on a road trip and you take where you were 10 hours ago versus where you are now, you'll find your average speed over the last 10 hours. Another example that typically gets used is something like you're measuring the amount of a drug in your bloodstream, like ibuprofen or something, and you have a concentration at one point, and then 10 hours or 5 hours later, it's now lower. What was the average disbursement of the ibuprofen and stuff like that? That is what the average rate of change is. But then mathematicians said, well, what if I want to know what's happening right now? So instead of taking 2 different points, what if I try and find a line right at now? And so if you've ever, if you looked at your car and you've looked at your odometer, that's calculating your velocity. And velocity is the derivative of your position. We'll talk about that soon. But it's that brings up the constant of a tangent line. What if we were to make those 2 points virtually indistinguishable? What if we were to make them the same point? What would our line look like? So I've got a couple pictures here. So this is our A, and this is our B. And if we were to draw this line, it would look something like this. So pretty close to A. But if you were to draw, as we see on the last problem, if A is right here, if A and B are the exact same point, we end up looking like our tangent line looks like this. So that distance of B was not enough to give us an accurate representation. So we get closer. We make A and B right here. And then the line becomes a little more accurate. The line becomes a little more accurate, but it's still not accurate enough. And so, do you see how this relates to unit 1? What we're trying to do, it's okay if you don't. And this is like, so a lot of students do wonder why we talk about limits. Like, how is this relatable? And the fact is, the derivative is created by looking at a limit. We are taking the limit as A approaches B. As your A's get closer or as your B's get closer and closer to A, what happens to your tangent line? What is the slope of that line? So that is how, we would not have the concept of a derivative if we did not have the concept of a limit. Now, fair warning about that. I'll get to it in just a second. So let f be a function, and then the derivative of f, which is denoted by f and then an apostrophe x. So the derivative of f, which is denoted f and then apostrophe, and you say f prime. You can either say the derivative of f, or you can say f prime, and we'll see some other terminology that you can use as well, but that's the two main ways that we say it. We either say the derivative or we say f prime. F prime and derivative are synonymous. They mean the same thing. So the derivative of f is denoted as follows. There is the way that we will use it, and then there is the formal way, which is still important, but more important for later on in mathematics. But so we say f prime of x is equal to the limits as h approaches 0 of f of the quantity x plus h minus f of x divided by h. Or the limits as t approaches x of f of t minus f of x all over t minus x. So Enstrom has an excellent question. And the thing is, are these the same equation? And painstakingly, yes. I had to prove that in my graduate class that those two things are the same, and it's annoying. It's annoying as all get out to prove that those two things are the same, but they are. It's just two different ways to represent it. Now, the secondary way makes more sense when you're looking at the construction. So imagine instead, I could have just as easily written this as b approaches x. And so f of t, you could also write f of x minus f of t over x minus t, but that's just the formal way of saying it. So you're looking at the slope of the line at x, the average rate of change as t and x are getting closer and closer together. So you're watching these 2 points get closer and closer together. Now that is the formal way. That is the original definition of the derivative. And it is useful. It is useful in proving stuff. It is very, very useful in that aspect. Basically, if you have to prove anything about the derivative in a math class, like an upper division math class, you want to probably use this definition. But when you're actually trying to compute derivatives with the definition of the derivative, this is far more useful. This is far more useful in that aspect. Now, How are they the same thing? How are they the same thing? I want to show you. So you don't need to write this down. But what if instead of A, I said X? What if I just said X here? And H is some number. Let's just say that it's a slightly larger number because we're doing f of X plus H. Then maybe this value here is X plus H. Just a little bit more than X. So you're going to make H go, if H goes to 0, H gets like X plus H gets closer and closer and closer until they become virtually indistinguishable when H finally goes to 0. And so if you're thinking about that, this is f of X. This is f of X plus H. So you're taking the secant line. You're doing like you have this point, which is X comma f of X. And you have this point, which is X plus H comma f of X plus H. And so you're doing y sub 2 minus y sub 1. So f of X plus H minus y sub 1, f of X, over X sub 2, X plus H, minus f sub 1, or X1, excuse me. The X's end up canceling. And you get exactly what I have right here. The numerator stays the same, f of X plus H minus f of X over H. That X plus H ends up canceling itself. That is how that formula comes to be, is you are legitimately, instead of just using A and B, one of them is X, one of them is X plus H. I probably should introduce it like that in the future, but hindsight's 2020. I will learn from my mistakes. So, anyways, that is the formal definition. And this is probably the more important way to see it. I will try to make sure that like I don't usually use this terminology unless absolutely necessary. You can use that, but as I said, for computing limits, the first way is far more useful. This was a specific version of it. Or sorry, this was the general derivative for any X value. If you want to find the derivative at a specific A value, you would use A instead of X. So you'd say f prime of A. I need to give more space here. F prime of A is equal to the limit as H approaches 0 of f of A plus H minus f of A divided by H. The only thing that's changed is I've replaced the X's with A's. You'll see a problem probably a little bit later. As a small little note, just for terminology's sake, just because it hits the ear wrong. We are taking the derivative, and as the process is called differentiation, we are not deriving the function. We are not deriving f. We are taking the derivative of f. Because deriving f would mean you're coming up with the formula for f, which is not what we're doing. We're finding the derivative. We're taking the function and using it to find the derivative through a process called differentiation. So just so that you sound mathematical when you say you're not deriving the function, you are taking the derivative of the function. You are differentiating the function. Is that okay? Just for terminology. And then here's the thing as a small little history lesson in mathematics, because this one's really, really cool. So you've probably heard of a person named Isaac Newton, correct? Pretty big, kind of a big deal, right? Like he's okay. He invented, like he thought of gravity and stuff, not a big deal, like whatever. So like you know about Newton. And if you've listened to Neil deGrasse Tyson or whatever, you'll hear him talk about Newton, and he has a big crush on the guy. He says like Newton invented calculus. And that's true. Isaac Newton did invent calculus, but at the exact same time, there was another person named, pretty sure, like I always mess up his first name, but I believe it's Gottfried and Leibniz. Was his name, and he was figuring it out in a different area in Europe. I can't remember where he's from. I think it was maybe Germany, or whatever. It doesn't matter. But he was discovering calculus at the exact same time at a different location in Europe. So these two people, like, imagine this is back in like the 1600s or even earlier. I always forget this part of it, but this is before you couldn't Snapchat each other or whatever. You couldn't be like, "Lol, look at my formula," and then like have him react to it with a emoji face or whatever. You can't do that. So they didn't really know that they were finding it out until later on. They finally started works were being presented, and it ends up being that they had two different ways of thinking about it. Newton was using a limiting process. He was using this definition. He defined the derivative as a function, as a representation of f, like f of x plus h minus f over h. That's what he was doing. Leibniz was doing a slightly different approach. Do you guys remember the terminology delta x and delta y? Do you remember what that meant? If you don't, it's no big deal. Delta x is meant this distance right here. So you don't need to write this down, by the way, but so I'm just writing this distance, the distance from here to here. What? Mike. I don't know why. Okay. Share content. Apparently my internet went out on my computer, my iPad. That happens sometimes. There we go. Cool. Thank you. So delta x right here, that's that distance. And so what Leibniz was thinking about it, he was thinking about the slope of a line as a rise over a run, of a value over a value, right? That's what we look at. When we're looking for rise over run, we find how much we move to the right, how much we move up. We take the quotient of those two things. So that's the delta x. And this right here would be the delta y. And so Leibniz was thinking about it this way. And what he was thinking is saying, well, what if we made that distance go to 0? What if we made delta y, like if we make delta x get smaller and smaller, if we make this distance right here, if we keep going closer and closer until it's virtually indistinguishable, you'll notice that delta y gets smaller and smaller. So if we're right here, as per usual, that's what delta y is. But if I instead do here and here, then this is delta x, and the corresponding thing would be right there. So delta y would now be like this big. So you see, as delta x gets smaller and smaller, delta y gets smaller and smaller. And so what he's decided to do is, instead of he made his own concept of a limiting process. And what he said is, if we're going to make them become 0, if we're going to make the difference nothing, if we're going to make the delta x be basically nothing, he created a concept which he called an infinitesimal. He called it dx instead of delta x. So delta x is a finite distance. Dx was talking about the infinitely small change in x over an infinitely small change in y, which he called dy. So that is another notation. So Leibniz was creating a calculus at the exact same time, and so he wrote it as dy dx. That is another way we write the derivative. He wrote it as dy dx or df dx, meaning an infinitely small change, an infinitesimal small change in f over an infinitely small change in x. Or some people even write it like this, or d dx of f of x. Or some books, really, really old textbooks, will write that. Really old textbooks may write it that way. Don't worry about that one too much. That can become useful in Calc 3 and beyond when you start dealing with multiple derivatives and what to do then. That's way down the road. So that's for later on in your mathematical career. We will see in particular f prime dy dx or df dx or ddx of f. So fun fact about that. Newton's definition, while easier to compute derivatives, it doesn't give the same intuition. And as an aside, dy dx, that's that thing. It's not a fraction. Not technically a fraction. Because it's an infinitely small change, it's an infinitely small value, which means it's like, because it's dealing with infinity, it's not actually something we can divide by. It's more of an intuitive idea. So dy dx is what he used to represent it. dy dx by themselves are thought of as those infinitesimals, but we cannot actually divide it. So here's the thing, though. If you think about it like a fraction, which is what his nation was doing because they were following his rules, because in England, everybody was goody-goody with Newton. They're like, man, he's our coolest guy ever. But in the rest of Europe, he wasn't as well known. Still important, absolutely, but Leibniz's notation led to a lot more intuition as to what the derivative is. It's an infinitely small change in y over an infinitely small change in x. And therefore, what ended up happening, so here's the history lesson, is that at the time, Newton was creating it, and Leibniz saw that he created it too and said, hey, I'm working on a similar concept. I think it might be the same. Do you want to get together and like hash it out, bro? Hashtag work together. That's what he did. He sent that in his letter. And Newton said, forget that noise, as the kids say, right? Do you guys still say forget that noise, or is that old school terminology? That's not he said that's not a vibe, and that was what that's how he ended it. Newton did not want to work with Leibniz for whatever reason, not sure why. The textbooks usually and the historic texts don't really explain why that happened. Could be that Newton was just too busy inventing other stuff. But anyways, the fact of the matter is that the rest of Europe was following Leibniz's definition, whereas England was following Isaac Newton's. And as a consequence of that, the rest of Europe was far more advanced in their mathematical understanding. They actually ended up proving a lot more things than England did at that time. If you look at a lot of the big names in mathematics of that era, it's all Italians, Germans, French, Swedish, and so on and so forth. Leonhard Euler, not English. Euler is one of the most important mathematicians ever. Emmanuel Galois, not English, French. Augustin Cauchy, French. All these people took Leibniz's definition and were able to extrapolate on it because it was such a vivid idea to them. The other one that I think of is the Bernoulli brothers, which are three brothers, I think, from Italy that have their hands in everywhere in mathematics. They're like super strange. The Bernoulli brothers, they're just three brothers that all are studying mathematics. Super weird. Like they didn't want to do anything else, I guess. Like they all wanted to be studying the same thing, which I don't know. I would feel weird with my brother doing that. Feel weird like trying to compete with my brother in that way. I don't know. Anyways, the point being is that because of Leibniz's definition, the rest of Europe was advancing far faster in mathematics than England was. So I say that to make the connection that we want to be able to use both formats. We want to understand both formats, the f prime, which is what we use typically when we're trying to compute things, and then when it comes to proving things and understanding why they work, we usually use the dy dx. So we will use both of them interchangeably. Most textbooks do, because depending on the situation, one way may be better than the other. So sorry to go on a little tangent, but I hope that was interesting at least about Newton and Leibniz. Most mathematicians prefer Leibniz over Newton in that aspect. Other scientists, of course, like Newton over the other one. But anyways, so when we're computing the derivative, this is the key fact number one. When computing derivative, by the definition, DEF apostrophe N meaning definition, when you're computing the derivative by the definition, you're not done simplifying. You can't take your limit until the h in the denominator has been canceled. Cancel culture. That's not a good joke. That's a terrible joke. That's low hanging fruit. That should be ashamed. When computing the derivative by the definition, and what I will say is that this is a rite of passage. We're going to find the derivative the hard way, the way that it started out. And then after this section, we'll start learning the rules that make the derivative way faster. But it is a requirement, and it is a rite of passage in mathematics. One might say that almost every calculus class across the nation, when they the exam that has derivatives, almost always has a question about the definition of the derivative. Hint, hint, wink, wink. You all see what I'm saying? Saying it without saying it. Maybe this might be something to make sure you know how to do on the next exam. Not this upcoming exam, because that's unit 1 stuff, but this is unit 2 stuff. Knowing this stuff might be important on a problem on your exam. Just saying. So the point is, you don't want to drop the limit sign. You don't want to compute your limit until you have canceled the h. And that makes sense from thinking about limits, right? If you're trying to find this limit, you're going to be dividing by 0 so long as this h is here, you're going to be dividing by 0. And we saw that that was a big problem. Whether it meant that we had to factor cancel, or it meant that we had to figure out, plug in a test value to figure things out. So find f prime of x for the function f of x equal to x squared minus 3x plus 2. So if you want to memorize a formula, one of the easiest ways to do so is to write it down every single time you do a new problem. In your notes, in your homework, like in the practice problems you do, anything like that, rewrite it down. I guarantee you, you'll write it enough times that you'll just start to memorize it. So this one, f prime of x. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Okay. Now, I didn't get, sadly, on our first day of class, I didn't get to talk about this, but this is a very, very big place where students make algebra mistakes. More specifically, pre-calculus mistakes, but I want to talk about it. John Doe student writes this. So don't write what I'm writing in red. Do not write this thing that I'm writing. F of x plus h. He writes that's x squared minus 3x plus 2 plus h. Why is John Doe student wrong? Think about it. F of the quantity x plus h versus this right here. What I have written is this. Because this is f of x, this is plus h. F of the quantity x plus h, you're plugging in x plus h into it. So the correct way to compute f of x plus h, which I'm going to do on the side here, if you feel comfortable doing it, do it as you go along. But I find that when students first start off, it helps them to find f of x plus h separately. So that's asking a lot to keep in mind if you do it the other way. So f of x plus h is x plus h squared minus 3 times x plus h plus 2. You guys see the difference? Versus, once again, I'm going to write this so you can see the difference. Versus f of x plus h is x squared minus 3x plus 2 plus h. Please take note of the difference. F of the quantity x plus h is what I wrote in black. F of x plus f of the quantity x then plus h is what I wrote in pink. And the reason why I make such a big deal about this is that if you do this, excuse me, if you do the pink, you will not get the problem right. You will straight up get stumped. You will get lost every single time, and you will not be able to finish the problem. You will not be able to cancel the h, which means you will not be able to take the limit. Every time you try and do f of x plus h, there is only one situation where that will be true, where you can do that and you'll be fine. And that is with f of x. The only time that it ends up being the same is f of x equals x. If you've got that function, it will work out. But that's the only function that it'll work out for. Otherwise, if you do the pink, you will get the problem wrong. Straight up, no ifs, ands, or buts about it. I will give you a 0 on the problem because that is not f of the quantity x plus h. Is that clear? Does everyone see the difference? It's important to know. So, I recommend computing this off on the side. This is x squared plus 2xh plus h squared minus 3x minus 3h plus 2. Don't forget that you have to FOIL the x plus h squared. Remember, that has to be FOILed. You do x plus h times x plus h. That's where that middle 2xh is coming from. So, I realize I'm saying, is that clear? I sounded way too aggressive in my tone. I want to make sure people don't have questions, right? It's okay if you ask questions about that. Is everyone okay with the difference between f of the quantity x plus h and f of x plus h? You know, good with that? Okay. So now that I've found what f of x plus h is, I can plug that into the formula. This is the limit as h approaches 0. Notice that I'm not dropping the limit sign because I haven't taken the limit yet. Just like before, I didn't take the limit until I got rid of the problem, right? If there was a common factor, I had to cancel that out first. I need to cancel that h before I can actually take my limit. So this is x squared plus 2xh plus h squared minus 3x minus 3h plus 2 minus, and once again, please put the function in parentheses here. Like the first piece, you don't necessarily need to put in parentheses, but the second piece, it does need to be. Please don't make that mistake. It breaks my heart. It breaks my heart when students forget the parentheses, because if you forget the parentheses, you will not distribute. So this is minus parentheses x squared minus 3x plus 2. I hope you can all see. I'm going to erase the parentheses for a second to show you why it's a bad idea to do so. So all divided by h. Hopefully you guys can see if I get rid of the parentheses, isn't this a bad thing? Because I will forget. I trust you that if it was you and there was nothing else going on, you would probably remember. I totally believe you. I totally believe that you would probably know what was going on. You'd remember to distribute. But I don't trust your environment. It could be that someone sneezes in the wrong way, has a really weird sneeze style, like if you've watched Community, like Pierce doing the like the crazy sneezes or whatever, or someone does something weird, or God forbid someone knocks on the door and says that you have to get out because there's an active shooter at the UNLV campus. That was crazy. That type of a situation. That was way too dark. I'm sorry. I should not have gone that dark. That was far too dark, and I do not like that I did that. Sorry. But I don't trust your environment. Please put the parentheses so that you remember to distribute. Okay? So you remember to distribute, and I'm going to skip some algebra and notice that if I do that, I'll have a positive x squared minus an x squared. So those x squareds cancel. I'll have a negative 3x minus a negative 3x or a plus a 3x. So those cancel. And then I'll have a plus 2 and a minus 2 because it's going to be the minus sign is going to be distributed, making it so that that term is also canceled. And isn't that nice? All the terms of f of x got completely canceled. That's pretty cool. That's pretty nifty. And so we end up with the limit, and leave a little bit of space, like in between these things. Leave some space here because we're going to write the factorization of it right above it. So the limit, notice that I have not dropped my limit sign because I haven't taken the limit yet. Yes, I know it is tedious, but it is required because if you say that it's equal to an expression, that is not mathematically valid. So you get 2xh plus h squared minus 3h all over h. Any questions so far? Okay. Sadly, there's a lot of algebra mistakes that can happen here, by the way. There's a lot of algebra. So, and I want to make sure I nip all the common mistakes that I see in the bud right now. So, John Doe student does this. So don't write this down, just pay attention. John Doe student does this and calls it good. Why is John Doe student wrong? There's still the h squared and the 3h. What I'm doing right here, which is not correct, is I'm taking a factor in the denominator and I'm canceling it with a term in the numerator. You cannot do that. You can only cancel factors. So what I have to do is notice that every term in the numerator, all three terms have a common factor of h that I can pull out front. So this right here, let's use blue. We haven't used blue. This right here is h times 2x plus h minus 3. And then I can cancel the h's because now it is a factor. It tears my heart apart when I see a student do what I just did with red, because then you were so close to the answer. You were so close. You were just one more step and you would have been done. And you would have gotten a full credit, but then I got to take away points. And I don't like taking away points if I don't have to. So the h is canceled. Now I know that I actually can take the limit. I'm going to do one more step, but if you felt comfortable just plugging in h equals 0, be my guest. But I'm going to do one more step. This is equal to, wrong color. This is equal to the limit as h approaches 0 of 2x plus h minus 3. Because the h and the denominators cancel, and we look at this just like normal. X is a variable. It's in the limits perspective, it's only caring about h. So it doesn't care about the 2x. It can just ignore it. It treats 2x as a constant. So this becomes 2x plus 0 minus 3, or preferably f prime of x is equal to 2x minus 3. And that is your function. That is your derivative. If you feel comfortable skipping algebra, please feel free to do so. I'm just showing every nitty-gritty detail, okay? And it took a lot longer also because we were talking about the common mistakes that students make. We're not going to do f of the quantity x then plus h. We're not going to do that. That's going to ruin everything. We're always going to do f of the quantity x plus h. You're going to change x in the formula to an x plus h. So this one, find dg dt if g of t is equal to 1 over t plus 3. I deliberately changed the variable to show us that it doesn't matter what the variable is. So by the definition, dg dt would be the limit as h approaches 0 of g of t plus h minus g of t divided by h. I'm writing it again. On an exam, you don't need to write it. On an exam, you don't need to write it. But I want to write it every time in our notes to give you practice with it. And I really think that if you're doing any homework problems, you should definitely write down the definition every time so that you get free memorization. If you rewrite it, it's just a free way to get more time to memorize it. Just you're training your brain to write it down. So off on the side, I'm going to calculate g of t plus h. Though you don't have to if you feel comfortable skipping that step, but that will be 1 over the quantity t plus h plus 3, or more specifically 1 over t plus h plus 3. Either way would be fine to leave it in, but saving yourself 2 extra pen strokes might help you in the long term. So that leaves us with equals the limit as h approaches 0 of 1 over t plus h plus 3 minus 1 over t plus 3, all divided by h. So as the key point number 1 says, we are not done. We cannot take the limit until that h in the denominator is canceled. It will always cancel for this class. If it doesn't, it means that you've done something wrong. And that's just one of the really cool things about the derivative is that for every function that we see in this class, pretty much all of them are differentiable. They have a derivative. So in every situation, the h ends up canceling, which is pretty nifty. So how do I get the h to cancel? Look at this. Can't be done. Try. No, throw out an idea. What would you do? So we need to take care of those denominators. Yes, we can't do that until they're all one denominator. So we need to find a common denominator. As I said before, if you want to, this is a complex fraction. It's a fraction with fractions in it. And so there's 2 main methods to simplify those types of things. You are free to do whichever one. I'm going to stick with method 1, which is finding a common denominator in each separate section. But I will tell you that the method 2, where you find a global common denominator, is far faster. So if you want to know that trick, let me know. But the more intuitive way that many students see it is finding a common denominator. So for the first term, it's missing a factor of t plus 3 over t plus 3. And the secondary term is missing a factor of t plus h plus 3 over t plus h plus 3. And that allows us to get to this, the limit as h approaches 0 of t plus 3 minus, in parentheses, t plus h plus 3 all over t plus 3 times t plus h plus 3 all divided by h. Though if you want to put the h, if you want to make this into a singular fraction and put that h in the denominator of the big numerator, you can do that. If you wanted to skip that step, that's fine. So I'm going to simplify the numerator. I'm going to combine like terms, but I'm not going to FOIL the denominator. I want you to think about why that would be the case. It's like yes and no. So the h is going to cancel out at the very, very end. So at the end of the day, once everything has been done, I'm going to be just plugging in h equals 0. So I could FOIL out a binomial times a trinomial. I could do that. But at the end of the day, hypothetically, what's going to end up happening is that the numerator and this h are going to cancel somehow. You'll see that in a second. And then we'll be able to cancel that at h. And then if I spend the extra time foiling that out, that's more chances to make stupid little math errors that we all make, you know, here or there. There's more chances to make those errors. And also it's not going to help us in the long scheme, in the grand scheme of things. So what I would recommend instead is just leaving that denominator unsimplified. Just leave it in factored format. So I'll say, like, for this, going to plug in h equals 0 at end. So why bother? Numerator, though, the reason for that is, imagine that this h in the denominator is going to go here. So it needs to be able to cancel with an h in the numerator. That's why I'm simplifying the numerator, but not worrying about the denominator. Anyway, so this will become, once that minus sign is distributed, you will end up with the limit as h approaches 0. I still haven't dropped the limit sign because I haven't taken the limit. The t's cancel, the h sticks around, so it's negative h, and the 3's cancel. I'll even write that. So we just have a negative h up top, and then in the denominator, we have an h times a t plus 3 times a t plus h plus 3. And isn't that nice? The h's cancel, and I'm just left with a negative 1 up top. So, last but not least, this will be the limit as h approaches 0 of negative 1 over t plus 3 times t plus h plus 3, which then I have canceled the h. You could skip this step and go straight to the answer if you want to, but I'm not going to for our notes so that they're completely listed. And so this will be negative 1 over t plus 3, and then t plus 0 plus 3, or preferably dg dt, the derivative of g with respect to t, is equal to negative 1 over t plus 3 quantity squared. Any questions on that? So I was able to drop the limit sign at the very, very end when I knew that the h in the denominator was finally canceled. So if you want to go straight from this step right here to here, or from here to here, be my guest. If you feel comfortable skipping a few algebra steps, I encourage you to do so. But any questions? Okay. We're gonna set up the other one, and then we're gonna set it up, and then we'll call it good. Remember, all of Unit 2 is on the next exam. So none of this stuff that we just went over in Unit 2 is on the exam. Unit 1.5, Section 1.5, that is on the exam. But anyways, so dy dx is equal to the limit as h approaches 0 of y of x plus h minus y of x divided by h. Yes, it says y equals, it doesn't say y of x, but it's a function, and so you can list it as a function. You can say y of x. And so, if you feel comfortable, once again, plugging in, like finding y of x plus h, or f of x plus h, or g of x plus h at the same time as computing the limit, be my guest. But if it helps you, like it does for me, I like to find it off on the side. Y of x plus h equals the square root of 3 times the quantity x plus h minus 4, which is sufficient. You can leave it like that. You can leave it as is, or you can write it as this: 3x plus 3h minus 4. Any questions on that? Then we're gonna write it down, and then I will let you guys fill in the rest of the details. I'll write the answer when we come back from our notes next week, since Wednesday will be the exam. But I want you guys to think about how you would go about doing it. This will be the limit as h approaches 0 of the square root of 3x plus 3h minus 4 minus the square root of 3x minus 4, all divided by h. And how would you simplify that? We've seen these types of things before. Square roots. This will help you for the upcoming exam because I guarantee you something might show up like this. I'm not saying it will, but I'm saying, I mean, you see like there's problems in the on the exam review that involve square roots. How do we deal with those? Conjugate. Sorry, what's the name again? Adriana. Adriana's correct. Conjugate. So this is how you would solve this problem. You'd multiply by the numerator's conjugate. So 3x plus 3h minus 4 plus the square root of 3x minus 4. But you can't just multiply the numerator. You have to multiply the denominator by the same thing. 3x plus 3h minus 4 plus the square root of 3x minus 4. I will leave that to you to enjoy over the weekend to figure out. I will finish the details later, okay? If you have any questions, please feel free to ask. Otherwise, I will try to be available via email as much as possible today and tomorrow before your exam. I have my office hours, building A, so right across the street, room 160D from 12:30 to 2:50 tomorrow. Yeah. Otherwise, also you can send me emails. I'll be posting the exam solutions the exam review solutions very soon, along with the quiz solutions a little bit later today. I'll email you when I do. Okay. Have a great rest of your day. Happy studying, and I'll see you on Wednesday.